Assalamualaikum and good day. So today we're going to continue the other parts of the chapter 2 part 3 concerning ZENER diodes. Okay, today we are going to cover until ZENER diode load regulations. Okay, so without further ado, let's start. Okay, so let's recap before we continue. So we have gone through on the IV characteristics and datasheet for the ZENER diodes. Okay, so now we're going to continue for the limiting ZENER. Okay. Oh, I didn't know the results. Okay, so today we're going to continue here. Okay, from here. So this ZENER analysis. So let's recall that ZENER diode is designed to specifically operate in the breakdown regions. Okay, if it's forward bias, it behaves just like a regular diodes with diode drop, for example, 0.7 for silicon, 0.3 for germanium. Okay, and if it's either case, short circuits, okay, or open circuits. So that one is short circuit is for the ideal diode for the for bias. However, for the ZENER diodes, we are more interested in the breakdown operations, okay, where the ZENER diode is designed for. Okay, so it's operate in reverse region and specifically breakdown regions. Okay, so this let's see from these circuits. Okay, so you have Vs as the source voltage and R is the resistor, and this is your ZENER diodes. Okay, and this is your load resistance. So if you can see, the polarity of the ZENER diode is actually in the opposite polarity of the V out, because we want the ZENER diode to operate in breakdown regions. So these are opposite polarities. In terms of the VZ, okay, in terms of VZ, this would be the positive and the negative for the VZ. Okay, if we are referring to the if we are referring to the normal diodes, okay, the regular diodes, okay, this one is VZ. If I are referring to the regular diode, it will be positive and minus. This one is for the regular diode. However, we are more interested for the breakdown region, which is in reverse bias for the ZENER diodes. Okay, so assume the ZENER diode is off, okay, because it is opposite polarity and we want it to be in the breakdown region. So assume the ZENER diode is off. Then we can replace it with an open circuits. Okay, with an open circuits. Find the voltage across ZENER diodes using the voltage dividers. Okay, so what is the VZ? Okay, we can use a voltage divider for finding the specific VZ at any configurations. Okay, so if our V naught, okay, V out, if our V out is less than the VZ, okay, then the diode is off. Okay, because when the ZENER diode is off, okay, ZENER diode is off, you replace it with an open circuit. Okay, and you will need to find the voltage across the ZENER diode. When the value of the voltage found, let's say if it's much less or less than the VZ, okay, the voltage of the ZENER diode operate in the breakdown regions. If it's less than that, the diode is off. Okay, if V out greater than VZ, the diode is in breakdown, which is on. for VZ. This one is actually referring to the VZ. Okay, so because you intend the ZENER diode to be operate in the breakdown region, so it is on, consider on when it is in breakdown region where the V out is much greater than the VZ. Okay, this one, if V out is less than VZ, so the diode is in off state. This one is referring to the SEM, is referring to the ZENER diodes. Okay, because if V out less than VZ, okay, V out less than VZ, what will happen? Okay, is it forward bias or reverse bias? Okay, try to answer this question. Okay, next we go to this clipper. For the case of the regular diodes, okay, just for recap, and later we're going to compare the clipper with the ZENER diodes, which is actually designed for the breakdown region again. Okay, so this one is clipper bias circuits. Means we have a bias, we have an external bias applied through in conjunction with our diodes. Okay, so the diode models I use is 1N4001. Okay, let's put all the things first. Okay, so clipper using regular diodes. Okay, it's not ZENER diode. We go to this regular diodes first, then we extend to the ZENER diode afterwards. Okay, clipper using regular diode needs battery to limit the AC voltage. How this one is being limited? How AC voltage is being limited? If you see, the V out is measuring at the outputs of here at the end with, for example, positive and negative. Okay, so at the positive cycle, which is the 10 volts, okay, at the positive cycle, so for the positive, let's say you have positive, negative here, negative, so this diode is on. Okay, this diode is on while this diode is off. Okay, so what is the V out taken? So we have 5 volt plus the voltage drop if it's a diode, if a practical model. So that's why you have, for the V out is actually 5 plus 0.7. That's why you have this number. And the next, if in the V in is at the negative cycle, so we're going to have opposite polarity. Okay, at this stage, negative, positive. At this stage, this diode is alternately off and this one is on. So since you still have it out measuring positive here, negative here, and since this one is reverse polarity, so positive, negative, then you have another positive, negative. So it is 5.7 volt. However, because V out is measuring in the opposite polarity, so that's why you have negative 5.7 here. Okay, so in the end, the clipper with the regular diode, you have the shape like this. Okay, batteries are not perfect if for the limiting the AC voltage, because many reasons. One of it is bulky, means we have additional components bulky to the circuits, and we have run down in time, and this one can leak nasty chemical, because if you notice, if you try to open, or you can try to see if the battery is overused or long time usage, you will see a chemical some chemical may flow out from the batteries. Okay, so this is the limitations of using batteries. Okay, so next we are going to discuss with the clipper circuit as well. However, we're going to replace it with a ZENER diode. Okay, so imagine these 3 conditions. Okay, imagine 3 conditions with A, B, and C. Okay, so if you see from the positive cycles, okay, the positive cycle, which is this one, so we can see that the ZENER diode is actually being turned on because it's opposite polarity, so it's operate in the breakdown region. So at this stage, the V output, okay, taken, okay, the VZ is actually positive, sorry, positive. Oh my god, positive. Sini. Oh, eraser. So we have some eraser here. Okay. So for the ZENER diode, because it's supposed to operate in the breakdown regions, okay. So here is how you draw label it. Okay, and this one is not VZ, and this one is VZ. Okay. So for the positive cycle of the input, so you're going to have the VZ is here. Okay, the V out is actually equals to VZ, and in the next cycle where the negative is here and the positive is here, the reverse polarity of our source, at this time the diode is actually being forward biased, just so it will behave like a regular diode. So since this one is opposite polarity with V output, okay, which is positive negative, so that's why you have negative 0.7 because opposite polarity. If it's germanium, you're going to have 0.3. So the same goes for this one, okay, the same as well. Your understanding here can be extended further to the circuits in B, and for the circuits in C is just like an addition of two ZENER diodes that have opposite polarities. So let's say we look in the positive cycle of the Vin. At this stage, which ZENER diode is on and which ZENER diode is off. So when we speak of ZENER diode, we are interested of it in the breakdown region where it's considered on. Okay, so this one is positive, this one is negative. So this D2 is actually the one that being on for the ZENER diode. Okay. D2 is on for the ZENER diode, so you have positive, then you have negative, VZ, VZ2 because it's due to diode 2, and D1 that time is turned on because it's forward bias. So you're going to have VD here. Okay, it's not VZ but VD. Okay, so positive, minus. So here at the positive cycle of positive, positive, negative, when positive. Okay, let me redo again because it's the slides make it confused when we are trying to label. So this one is the ZENER diode. When it is, this one is positive, so the ZENER diode having the V diodes, not ZENER diode. Okay, and then let's say we are using different colors now. Let's say for this one. So let's say in the negative cycle, okay, where you have negative here and positive here, what happens is that this diode D1 will activate the it's quite difficult to use this. So the next, if it's positive, negative, you can see that actually this diode is off. Okay, so it means that this VZ is on. Okay, VZ is on, and this one is actually being on for regular diode. This for say, so you're going to have VD here. Okay, VD. So you have positive So the next cycle for this negative, so this one VZ will be on, and D2 will be for bias. For it will show a regular diode application, not ZENER diode. So in terms of positive negative here, you're going to have the VZ sorry. So you're going to have this positive and negative in. So here, negative to here, so it will be like positive and negative of VZ. Okay, and then you have this one, which actually turn on, okay, turn on with a 0.7 volts, okay, 0.7 volt. Okay? So that's why you have this being enhanced, okay, VZ1 plus 0.7 volt. Okay, and the next one is negative VZ1 minus 0.7 volts. Okay, this one is coming from the regular diode operation, and this one is coming from the ZENER diode operation, which is the breakdown region, and this one is the diode drop. Okay, next we go to this ZENER circuit analysis. So we're going to analyze in three conditions. Okay, first is we fix the source and also the load resistor, means none change for this both parameter, the first condition. And then the next condition is where we're going to fix our source voltage, and we vary the value of RL, means RL is not constant. In this situation, it is referred to as load regulation, which we cover in these videos. Okay. Next is the third one where we have variable Vs, means Vs is changeable. However, with Rs is only fixed value. So this is line regulation. So we're not going to cover line regulation today. Okay. So we go to this voltage regulator. Okay. ZENER diode can act as a voltage regulator device because after the near voltage in the reverse bias, the voltage of the ZENER diode in the breakdown region relatively almost constant, relatively, because it's still up to changes, but relatively it is actually almost the same values. Okay, so that's why it's suitable for as to use as a voltage regulator device. Okay, next is maintains a nearly constant voltage, like I told you just now. Delta V or VZ is the voltage is not really changed, which is nearly constant across its terminal. So this is one characteristic of a regulator, right? Okay, where we want the things to have certain value consistent. Okay, so that we see from the two circuits. Okay, one is a simple regulator circuit employing VZ, and the next is a regulator circuit with your with addition of the RL resistor. Okay, so this is a simple circuit. So if you see, this one is a positive and this one is minus for this source voltage, and you see it's actually opposite of our diode, general diode. But since this is ZENER diode, so when this one is positive, this one negative, the ZENER diode is actually reverse bias, and until it reach and going to be constant, almost constant, for when it is in a breakdown regions, which is the opposite polarity. So this one is Vs, and this one is negative, and this one is positive for the regular diode. However, for VZ, it is the opposite. Okay, we have positive and you have negative. So why we need the RS? Okay, RS is to limit the Zener current so that it is less than the maximum current IZM. So the current that passing through the Zener diode must be actually less than our IZM. So IZM is a Zener current, okay, and we try to avoid this because we try to avoid the diodes for being to be broken. Okay, so the purpose of having RS is just a current limiting resistor. So next is how we're going to determine whether the Zener acts as a regulator or not. Okay. So first we assume means maybe it's short circuit, maybe it's open circuit, but we assume first Zener diode is in open circuits, which is in the reverse bias and also especially for the breakdown region. Okay. Next we're going to determine the load voltage across the Zener diode Vz. Okay, if our load voltage is much greater than Vz, if our load voltage is greater than our Vz, then that time the Zener diode is on. Okay, the Zener diode is on, hence VL equals to Vz. Okay, if VL is greater than Vz here. Okay. Next is our VL load is lower, if actually lower than Vz, the regulation does not occur and our load voltage will remain the same. Okay. Next, we're going to go to this voltage regulator for the first part of it, which is we fix the Vs and RL, means there is no changes in the load section where we're going to have resistance which is incredibly small. Okay, apply distributed and resistance are fixed. Okay, so first, sorry, just now this one is we fix Vs, it's RL, so not changing. So we determine the state of the Zener diode by removing it first from the network, because like we told just now, we assume the Zener diode is on. How Zener diode is on? It is actually in the reverse breakdown region. Okay, so we remove it, so it's like an open circuit. Okay, then we calculate the voltage across the resulting open circuits through voltage division rule or current division rule. Which one is more applicable? So this is, we can use a voltage divider rule. So in order to calculate this VL is actually RL over VI, RL times VI over RL plus R. So this one is the voltage divider. Okay, voltage divider circuits. Okay, as this one is series to one another, you can do series equation. Okay, so if our V, okay, if our applied voltage is greater than the Vz, then our Zener diode is on, because so Zener. However, if our V greater than the Vz, the Zener diode is off. It's just like a forward bias with small, not so much current. So for the on state, we change the color. The on state for the Zener diode. So if you have positive, negative here, okay, in terms of putting like a battery like state for easy works and imaginary. So if V is at here, okay, if you see here, it is for reverse bias. So actually the diode is turned on is turned on when it's operate at Vz much greater than the knee voltage. Okay, and the reverse bias regions, and since it's designed for breakdown regions, so opposite polarity is just that is a positive minus. Okay, next, if it's off, okay, it is off where your Vz, where your V, the value of voltage is actually in between the Vz until 0 volts, the diode is turned off. So you can see, right, if you have positive and if you have negative, the diode is like turn off. Okay. Next. Okay. Next, we go to this voltage regulator. Step 2. After that, we need to substitute the appropriate equivalent circuit and solve for the desired unknowns. Depends on what unknowns we want. It can be IZ, it can be VL, it can be RL, and so on. Okay. Wait for a while. I'm opening on turn on the aircon. Okay, next is the voltage regulator, step 2. Okay, substitute the appropriate equivalent circuit and solve for the Z naught. So for the on state diode, okay, the voltage across parallel element must be the same. So VL is equals to VZ. So this one you refer to the previous figures. Okay, for the on state diode, the voltage across parallel element must be the same. Where you have the voltage goes to ZENER voltage. The ZENER diode is determined by KCL, because if you see this is IZ equals to IR equals to IL. So it's actually, if we to rearrange it so that we can understand what happened, okay, IR is equals to IZ plus IL. Okay, IR equals to IZ IL. So IR is current passing through this resistor, and then it's split to this ZENER diode and also load. Okay, the power distributed by ZENER diode is determined by VZ times IZ. So this one, how, let we see, just to make you understand better. So let's say we go to the previous slide. So you can see, in order to get the value of this sorry, where is it? So IZ equals to IR plus IL. So we stick to this, IR equals to IZ plus IL. So because you have IR here, okay, IR here, then it's split to this VZ, okay, and VR. So that's why you have IZ and IR, IZ plus IR load, it equals to I passing through this resistance before it's being split. Okay. For the off-state diode, okay, if the diode is being off, the circuit equivalent circuit is just like an open circuits. Okay. So next we go to this load regulation, the final part of the recording today. Okay, in the load regulation, we're going to fix our VS. Okay, means VS is not changing, but we're going to vary the value variable of the value of the load resistance. So if you see, the word is get the RL mean, so that ZENER diode is on. So if it's the ZENER diode is on, okay, it means it is reverse bias, but because it's designed to operate breakdown region, so that's why we take this as a positive polarity and this as a negative polarity because of the operations. Okay, if so, get the mean so that ZENER diode is on. Okay, so what is the value of the RL mean so that our ZENER diode is can on? So if we calculate from this VL is equals to RL. This one is for the voltage, for voltage divider. So to get the value of RL is actually RL over RS plus RL time with the value of the voltage source. Okay, so this is pretty much just like KVL, and then rearranging this equation. So you will get this RL min, the minimum load resistance for the ZENER diode to be on. Okay, so if RL is greater than RL min, ZENER diode is on. Okay, so that VL is equals to VZ, with this one. Okay, if RL min, then IL min, then Z min because of constant I1. If RL max, then IL min and IZ max. You can see the difference here, right? So if our resistance is minimum, then most probably our current will be maximum. This is normal because let's say for V equals to IR. So let's say V is constant, then IR we can play. We can play with this IR. Okay, so if the voltage is constant, okay, if your RL min is high, means IL max will be low, okay, and IZ min equals to will be Z minimum because of the constant I1. If your RL max, for the RL max, because it's max, V equals to IR, let's say V is constant, R is maximum, then we have I which is maximum, okay, if RL max. Sorry, if let's say we go to this equation for general equation. Sorry. So if RL max, this one is getting maximum, okay, and this one because it's constant. So if this R is increased, this one will be decreased. So that's why if RL max, then IL minimum at that time, and because the IL at the load is minimum, then much of the current will flow through the diodes. So that time diode will have IZ max. Okay, so IZ min or IZ max, okay, whether it is a maximum or minimum depends on our configuration circuits and off and on and off. So for IZ min or maximum, so I pass into this one, one is constant and minus IL max over min. Okay, IZ max you can take from data sheet. When the IZ max maximum means literally at that time, the for IZ max at the diode voltage, mean if I is maximum means our R is minimum. Okay, so assume this one is, we make assumption if IZ min equals to 0, okay, means the value at which the currents the diode start to behave in breakdown regions. So this is IZ min. Beyond this or bigger than this IZ min, the diode is actually behave just like a regular diode. Okay, so where if IZ min is assumed to be 0, then we will get I1 equals to Vs minus Vz over Rs. You can try this at home for the previous circuits, which is the rule that we apply here is a voltage divider rule. And then for the IL max, after you get the value, okay, you will also notice that IL max is equals to Vz over the RL min, because this current is maximum at the load, means that in the min and the load part for the resistance it is higher, lower, okay, or RL max equals to Vz over IL min. So this one is pretty much straightforward. Okay, just try to take your time, try to see the example and retry it, okay, so that you know you understand or not. Okay, okay, so we have another 3 slides before I'm going to stop. Okay, so this another extension for this load regulation circuits. Okay, so you have, this is your V in, positive and minus, and the diodes for this kind of configuration. So the diode is actually in the reverse bias state, so it, if it's reached breakdown region, it is going to have the voltage of Vz. Okay, And you have IL here, which is variable due to this arrow symbol, means the resistance can be changed in terms of value. Then this is IT, which is I test. Okay, so when RL is infinity, when it is open circuit, means no current flow. Okay, we will have IL equals to 0. All current will pass it through this diode because this one is open circuits. So when RL is connected, okay, when we start to connect the diode, the current quantity is divided between diode and RL. Okay, between diodes and RL. As RL is increased, okay, as the resistance, load resistance increase, IL will be decreased. Okay, IL will be decrease because of V equals to IR, right? So if I is increased, if R is increased, I will be decreased. Okay, and IZ increase and vice versa. So it can decrease until IZ mean only. Okay, for the ZENER diode to actually operate in the reverse, in the breakdown region, so it need to have this value of IZ minimum. Okay, IZ minimum. For example, here. Okay, so then we have the equivalent value of VZ minimum as well. Okay. Sorry. If this is IZ minimum, so this is actually the voltage and the starting voltage for the diode to operate in the breakdown region for the ZENER diode. So I can decrease until as mean any lower than the diode will not able to regulate, because the diode at this time will not be a ZENER diodes. Okay, it will going to be like a regular diode. Okay, at IZ mean. Okay, so IZ mean, where we have the Z here is minimum. Okay, when this is minimum means logically the diode, the current passing through the load resistor will be maximum. So it's alternate. So this is quite straightforward. Okay, therefore RL must be minimum. Okay, to have an IZ which is minimum, you're going to have IL which is maximum. In order to have IL maximum, okay, in order to have IL which is maximum, you need an equivalent resistor, load resistor, which is much smaller, which is minimum. Okay, total current through R is constant because this one is not being splitted. It is actually current, is a current limiting resistor before the circuits of ZENER diode with the load resistance. Okay, so this one is the examples. Okay, so what is IL max and IL min to obtain regulation, and what is the minimum RL, then given rated value which we should be getting from datasheet. Okay, 1 mA is the minimum current ZENER diode current for it to operate in breakdown region, and then you have 50 milliampere, which is the maximum values. Then you have VZ is 12 volts. So if we are discussing about IL max, okay, if this current here is maximum, mean the current, if this is current is max. Okay, first is what is IL max. So if IL max maximum here, then IZ will be minimum. Okay, so and IL min, if this is IL min, okay, so this one will be IZ max, is alternately. Okay, next, let me try to discard. So let's see how the page. Okay, so taking this one out. Okay, so for IL, okay, let's say we have no current passing through this resistor, load resistor at that time. So because there is no current, means it's like an open circuit for the resistor. The resistor will be like infinity here. Okay, then you will have Iz is equals to Iz max IT. Why? Because majority or most of the current will flow through these diodes. Okay, so when we calculate in terms of voltage divider rule, okay, Iz max is equals to IT, okay, which is during this stage. So it's actually 24, okay, minus 12 and over 470, okay, which is equivalent to 25.5. Okay, so how we get this VZ? Okay, so this one is we get from here. Okay, and then because it is IL equals to 0, means Iz will become maximum. So this is the maximum rated value. Okay, then we, based on the circuits and calculation, we get the Iz max is equals to 25.5 microampere. So this one is good because the value is much less than the maximum rating, 50 milliampere. Because if we have 51, 52 or some value that is much greater than the maximum Iz max, then maybe our diode will be broken. Okay. So since our calculated Iz is actually much smaller than the 50 milliampere, so there is no worries. Okay, the diode is still operate in breakdown region. However, it will not be broken because the calculated Iz max is much smaller than the maximum. Okay, this value is less than 50 milliampere. So that's why RL for this case can be removed without disturbing the regulation. We still have regulation output even if we remove the RL for this case because our Iz max is much less than our maximum rating. Okay, so next, when IL max, okay, this one is IL is minimum. Okay, the most minimum is 0. Next is IL max, where is actually maximum. So when IL is maximum, with the maximum current flow here, means there will be minimum current flow at the ZENER diodes. Okay, so IL max equals to IT minus Iz min. Okay, IT, you get this threshold is 25.5 milliampere, and minus Iz min, which is this one, which is 1 milliampere, then you get 25.5 milliampere. Okay, then the next question, what is the minimum RL? What is the minimum RL? Means V equals to IR for the ohms law. Okay, V equals to IR. Then to get RL min is actually VZ equals to IL max, because if the resistance is minimum, means the current is maximum. So just like what we showed last time, okay, I think you know already. Because if we have V, if we have V equals to IR, okay, V equals to IR. So if we want to have RL min, so if this is minimum, so this one will be maximum. Okay, if this is minimum with current, so you go ahead to have a maximum resistor. Okay, provided that the voltage is constant. So minimum of RL, when we discuss about this minimum of RL, then that time our IL will be maximum. Okay, will be maximum. So that's why you have RA equals to VZ equals to IL over IL max. Why VZ over IL max? Because this one is parallel connection. Okay, so VZ is we get from the data sheet. So 12 divided by 24.5 milliampere, which is 450 ohms. Okay, the minimum resistance values. Okay. So this is the exercise. You can try to do at your own convenience. Okay, then this is the answer. Okay, please try it. Okay, and we will go through in the next class if we have additional times, free time to actually cover this exercise to discuss. Okay, so you have the answer here, so you can try. Okay, so the next of the parts of the lecture, whether we're going to do its recording or face-to-face, will be the line regulations. Okay, so just a sneak peek for the line regulations. The source now is going to be varied, and the RL will going to be fixed. Okay, so with that, we're going to end this recording until this part, and going to continue next time. Okay. Assalamualaikum, and thank you for listening.